Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to imagine, just for a second, the sheer kinetic force of a fast-moving tennis ball.
Okay.
You know, like you are standing on a court and someone just launched a professional, top-tier serve directly at your chest. We are talking over 120 miles per hour.
That is going to leave a mark.
Exactly. It's going to leave a severe bruise, maybe even crack a rib. You can hear that distinct, sharp thwack of the racket, and if you had a high-speed camera, you could actually visualize the ball warping slightly, like compressing from the impact as it blurs across the net.
Right, because it has immense momentum, a very real physical transfer of energy.
Yeah, physical, undeniable energy. Now, I want you to take all of that energy, that entire macroscopic wallop carried by trillions upon trillions of atoms, and shrink it down. Keep shrinking it. Compress all of that violent kinetic force until it is carried by a single, solitary, microscopic subatomic particle hurtling out of the sky.
It really forces a complete recalibration of how we perceive scale, doesn't it?
It really does. It breaks my brain a little bit.
I mean, you are taking something that exists in our everyday tangible world, this completely macroscopic transfer of energy, and compressing its power into a spatial volume so infinitesimally small that it completely defies standard human intuition.
Right.
We are talking about a concentration of energy that honestly challenges the foundational models of astrophysics.
And that extreme concentration of energy, well, that's the focal point of our deep dive today. We are going to decode a 60-year-old cosmic mystery regarding ultra-high energy cosmic rays.
It's a mystery that has frustrated the community for decades.
Totally. Because for decades, the astrophysics community has basically been staring at an impossible mathematical dead end. But recently, a groundbreaking shift in the theoretical framework led by astrophysicists like Maras has completely flipped the paradigm.
Yes, the Maras research really changes everything we thought we knew.
It does. There is this new, highly compelling theory suggesting that these space particles might actually be carrying ultra-heavy secrets. And if this holds true, it means we aren't just getting pelted by random cosmic debris. We are basically being handed a literal physical map to the most violent, explosive phenomena in the entire universe.
The shift in understanding here is just profound. For a very, very long time, we have operated under a specific set of assumptions about what these particles are actually made of.
Right, the building blocks.
Exactly. And those assumptions dictated where we thought they came from. By challenging the core identity of the messenger itself, we are forced to rethink the entire architecture of the local universe.
We're talking about looking at cosmic engines, these massive gravitational forges that make humanity's greatest engineering achievements look, well, microscopic in comparison.
We are trying to understand the extreme relativistic physics required to accelerate a single atomic core across billions of light years of intergalactic space without it completely disintegrating.
Okay, so let's ground this in a specific event. Let's go to the West Desert of Utah, specifically Millard County, where the telescope array project is spread out over roughly 300 square miles of just desolate terrain.
It's a massive facility.
Yeah, it's huge. So it's 2021, and this massive grid of surface detectors catches an anomaly that almost defies belief. They named it the Amaterasu particle.
After the Japanese goddess of the sun.
Right, which is a great name. This single invisible entity hit the atmosphere with an energy level of about 240 exaelectron volts. But, you know, throwing around the term exaelectron volts usually just glazes people's eyes over.
It's just a number to most people.
Exactly. So what does 240 eV actually represent physically?
Let's break down the scale. An electron volt is the baseline metric we use in particle physics. It is the amount of kinetic energy gained by a single electron when it accelerates from rest through an electric potential difference of 1 volt.
So a completely minuscule amount of energy.
Incredibly small. To scale up, we use the standard metric prefixes. A mega electron volt is 1,000,000. A giga electron volt is 1,000,000,000. A tera electron volt is 1,000,000,000,000.
Okay, following so far.
And an attalelectron volt is 1 quintillion electron volts.
Wow.
Yeah, that is a 1 followed by 18 zeros. So the Amaterasu particle arrived with 240 times that amount.
240 quintillion electron volts.
Right. Stated another way, 240 quintillion electron volts packed into one tiny atomic package.
Which naturally brings us to the Large Hadron Collider, because whenever we talk about high-energy physics, the LHC is like our human benchmark.
The pinnacle of human engineering.
Yeah, we have this 27-kilometer ring of superconducting magnets buried under the border of France and Switzerland. We chill it with liquid helium to a temperature colder than outer space. We spend billions of dollars and decades of engineering just to smash protons together.
It's an incredible machine.
It is. So how does our absolute best human effort compare to this Amaterasu particle?
Well, the LHC accelerates protons to energies of roughly 6.8 tera-electron volts per beam. When they collide, you get a center of mass energy of about 13.6 tera-electron volts.
Okay, 13.6 tera.
Right, and remember, tera is a trillion. Exact is a quintillion. The Amaterasu particle is about 7 orders of magnitude more energetic.
Wait, 7 orders of magnitude?
Yes. That means the universe, natively, hurled a particle at Earth with roughly 10 million times more energy than the absolute theoretical limit of the Large Hadron Collider.
10 million times.
Exactly. If you wanted to build a human particle accelerator capable of reaching the energy of the Amaterasu particle using our current technology, the ring wouldn't fit in Switzerland.
Where would it fit?
The ring would have to be roughly the size of the orbit of the planet Mercury.
Okay, that is just staggering, but this is exactly where my intuition starts fighting the math. Okay, let's unpack this. Let's go back to that tennis ball analogy.
Sure.
If a single subatomic particle is hitting the Earth with the macroscopic kinetic energy of a 120-mile-per-hour tennis serve, why are we not seeing the physical damage?
That's a very common question.
Right, because if I am standing outside in Utah and a particle with that much localized kinetic energy passes through my shoulder, it shouldn't just be an abstract mathematical event on a computer screen.
You'd expect to feel it.
Yeah. It should blow a microscopic hole right through my tissue or punch through the fuselage of a commercial airliner. Where does all that energy actually go?
The flaw in that intuition, and it's a very natural one to have, is assuming the particle actually reaches the ground or your shoulder intact.
Oh, it doesn't.
It almost never does. The Earth is wrapped in a profoundly dense shield, our atmosphere.
Right, miles of air.
Exactly. When a primary cosmic ray, like the Amaterasu particle, enters the upper atmosphere, it hits an air molecule, usually nitrogen or oxygen. Yeah. But to say it hits it, it's honestly a massive understatement.
What happens?
The collision is so violently energetic that it triggers a catastrophic hadronic cascade.
So it basically annihilates completely upon first contact?
Utterly. The primary particle is just destroyed, and its immense kinetic energy is instantly converted into mass, governed by Einstein's E equals mc squared.
Energy becoming mass.
Right. This creates a massive shower of secondary particles, things like pions, kaons, protons, and neutrons. Those secondary particles are moving so incredibly fast that they immediately collide with other atmospheric nuclei.
Creating like a third generation of particles.
Yes, then a fourth. The neutral pions decay almost instantly into high-energy gamma rays, which then interact with the electric fields of atmospheric nuclei to create electron-positron pairs, which emit more gamma rays, and the cycle just continues.
It's a runaway chain reaction.
A massive one. By the time this cascade reaches the ground, the original 240 exaelectron volts of the Amaterasu particle has been divided and distributed among tens of billions of secondary particles.
Tens of billions?
Yes. This phenomenon is known as an extensive air shower. The footprint of this shower can cover several square miles of the Earth's surface.
So the kinetic energy of the tennis ball hasn't disappeared. It has effectively shattered into a billion microscopic grains of sand raining down simultaneously over a huge geographic area.
That is a perfect way to visualize it. The detectors out in Utah aren't catching the primary particle at all.
They are catching the sand.
Exactly. They are catching those microscopic grains of sand, analyzing their arrival times and energies across the grid, and using computational models to reconstruct the exact mass and energy of the original obliterated particle that started the shower.
Okay, that clarifies the mechanics of the impact beautifully. But here is the massive historical context we have to establish for the deep dive. The Amaterasu particle in 2021 wasn't a total anomaly.
No, it certainly wasn't the first of its kind.
Right, it had a predecessor. A particle that fundamentally broke astrophysics back in 1991. The famous Oh My God particle.
Yes, detected by the Fly's Eye experiment at the Dugway Proving Ground, which is also in Utah, the Oh My God particle hit with an estimated energy of 320 exaelectron volts.
So even more energetic than Amaterasu.
Considerably more. When astrophysicists calculated that number back in 1991, They were in a state of absolute disbelief, hence the rather dramatic name.
And the reason they were in disbelief wasn't just because the number was high, right? It was because the number was supposed to be literally impossible.
That's right.
There is a theoretical speed limit in the universe for these kinds of particles, and the oh my god particle just shattered it. Let's talk about the GZK limit, because understanding this cosmic friction is the entire key to unlocking this new ultra-heavy theory.
The GZK limit, named after Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, who calculated it independently in 1966, is a theoretical upper limit on the energy of cosmic ray protons traveling through intergalactic space.
Okay, upper limit.
Yes, and to understand it, you have to understand the environment the particle is actually traveling through. We often think of the void between galaxies as completely empty.
Just a dark vacuum.
Exactly. But it isn't. It is saturated with the cosmic microwave background.
The leftover thermal radiation from the Big Bang.
Precisely. The universe is bathed in this fog of microwave photons. Now, to a slow-moving particle, these photons are completely harmless.
But what if it's not slow?
Well, if a proton is traveling at ultra-relativistic speeds, we're talking energies approaching 50 exactly electron volts. A very strange relativistic effect occurs.
Oh, interesting.
From the perspective of the hyperfast proton, those low-energy microwave photons suddenly appear blue-shifted. They appear as highly energetic gamma rays.
Basically a wall of radiation.
Exactly. And when the proton collides with one of these photons, the collision has enough energy to undergo a resonant interaction, creating a subatomic particle called a pion.
And creating that pion requires energy, which it has to steal directly from the proton's kinetic momentum, right?
Precisely. It acts like a quantum toll booth. Every single time the proton interacts with a photon, it bleeds off a significant fraction of its energy.
It's paying the toll.
Yes. The GZK limit dictates that a proton simply cannot travel further than roughly 50 megaparsecs, which is about 160 million light years, without bleeding its energy down below that 50 eV threshold.
So if we see a particle hit Earth with 240 or 320 electron volts, the GZK limit tells us a very specific rule. It could not have traveled from the deep, distant universe.
It's physically impossible.
Whatever fired that particle must be relatively close to us, cosmically speaking. It has to be sitting right in our local galactic neighborhood.
That is the inescapable logical conclusion. If it had come from billions of light years away, the cosmic friction of the microwave background would have eroded its energy long before it ever reached Earth. Therefore, the source must be nearby.
Which brings us to the great 60-year whodunit. Because if the source has to be in our local neighborhood, we should be able to just look up and see it.
You would think so.
Right. If someone shoots a flaming arrow into my yard, I look at the angle it hit the grass, trace the trajectory back over the fence, and find the person holding the bow. We have the arrival direction of the Amaterasu particle. So when astronomers trace the trajectory back into the local universe, what massive, violent, astrophysical monster did they find sitting there?
They found a void. A completely empty region of space.
A void. Just nothing.
Absolutely nothing. The inferred arrival direction pointed to an area known as the local void.
A local void.
Yes, a vast, relatively empty expanse of space bordering our local group of galaxies. There are no active galactic nuclei, no massive starburst galaxies, no obvious catastrophic engines capable of accelerating a particle to 240 electron volts anywhere near there.
Wait, hold on. If the GZK limit dictates that the particle absolutely must come from a nearby source because it couldn't survive a long journey.
Right.
But our tracing points to an empty void where no local source exists. How is the astrophysics community not panicking over a mathematical dead end like that?
Well, panic might be a strong word.
But it implies that either our understanding of the universe's structure is wrong or our tracing methodology is fundamentally flawed, doesn't it?
It definitely caused a profound theoretical frustration.
Yeah.
But let's examine the tracing methodology. You use the analogy of tracing a flaming arrow.
Yeah.
That assumes the particle travels in a perfectly straight line from its source to the Earth. But these particles are charged, and the universe is threaded with invisible, tangled magnetic fields.
Right, the galactic and intergalactic magnetic fields. And charged particles interacting with magnetic fields are subject to the Lorentz force.
Correct. The Lorentz force dictates that a charged particle moving through a magnetic field will experience a force perpendicular to both its velocity and the magnetic field.
Meaning its path gets bent.
Severely bent. So an ultra-high-energy cosmic ray traveling across millions of light years isn't moving in a straight line at all. It's moving in a vast, complex arc.
This is more like a curveball.
Exactly. To find the source, astrophysicists don't just point a laser backward. They have to mathematically unwind the deflection. modeling the strength and orientation of all the magnetic fields the particle passed through.
So the obvious answer is that our map of the universe's magnetic fields is just wrong. We modeled the deflection incorrectly, so we accidentally traced it back to the local void when, in reality, it bent entirely around the void from somewhere else.
That is definitely a critical piece of the puzzle, but it actually doesn't solve the core contradiction.
It doesn't.
No. Even if we introduce massive margins of error into our magnetic field models, we still can't find a local source that fits. The deflection of a 240 eeV proton simply wouldn't be dramatic enough to completely hide its origin.
Unless what?
Unless the intergalactic magnetic fields are orders of magnitude stronger than any of our observational data suggests.
Okay, so the flaming arrow analogy is completely failing us here, which means we have to re-examine the arrow itself.
That's where the new research comes in.
If the trajectory and the physics of the GZK limit make absolutely no sense for the standard type of particle we assume is hitting us, then the paradigm shift has to happen at the level of the messenger itself. We've been assuming these ultra-high energy cosmic rays are protons, single hydrogen nuclei. Why?
Simply because hydrogen is the most abundant element in the universe. It is the lightest, simplest building block out there.
Makes sense.
From a purely statistical and theoretical standpoint, it is much easier for an astrophysical engine to grab a proton and accelerate it to near the speed of light than it is to accelerate something massive. The models for acceleration mechanisms, like Fermi acceleration and supernova shockwaves, work very elegantly for protons.
But Kota Murasa and his colleagues at Penn State, along with the Yukawa Institute in Japan, looked at this 60-year void paradox and essentially said, the proton assumption is the poison pill in our models.
Exactly. Their recent research fundamentally changes the identity of the highest energy cosmic rays.
They propose that we aren't looking at single protons, we are looking at ultra-heavy atomic nuclei.
Specifically, nuclei heavier than iron. This is a radical departure from the standard model.
Because iron is huge compared to hydrogen.
It is. When we discuss an atomic nucleus, we are talking about the central core of an atom, governed by the strong nuclear force. A proton is just a single nucleon. An iron nucleus, iron 56, consists of 26 protons and 30 neutrons bound tightly together.
It's massively heavier.
Massively heavier, and it holds a significantly higher electrical charge.
The mass-to-charge ratio is key here, I think, because if I'm trying to picture why an ultra-heavy nucleus solves the paradox of the cosmic void, I keep coming back to the GZK limit, the cosmic friction.
Right, the toll booth.
Here's where it gets really interesting. Earlier, I used the analogy of a freight train and a lightweight sports car. The proton is the sports car. The microwave background radiation is a miles-long stretch of mud.
I like this analogy.
The sports car hits the mud, loses all its kinetic energy, and just stops. Therefore, it couldn't have come from far away. But an iron nucleus, the freight train, has so much sheer mass and momentum that it just plows through the mud, retaining its speed for much longer.
The momentum aspect of your freight train analogy captures the macroscopic feel of the theory perfectly. But at the quantum level, the interaction is actually much more intricate.
How so?
It isn't a physical slog through mud. As we discussed, it's a resonant interaction, a quantum tax. But how an iron nucleus pays that tax is fundamentally different from how a proton pays it.
Because the nucleus can distribute the impact across all its constituent neutrons and protons.
Okay, precisely. When an ultra-heavy nucleus encounters a cosmic microwave background photon, it undergoes something called photodisintegration.
Photodisintegration?
Yes. Instead of the entire particle bleeding out a massive percentage of its kinetic energy to create a pion, the photon might just knock a single neutron or proton loose from the heavy nucleus.
Oh.
The main core of the nucleus survives, continuing forward with a slightly reduced mass, but maintaining a staggering amount of its original relativistic speed. It is a slow chipping away, rather than a catastrophic braking mechanism.
So the freight train is slowly losing boxcars as it travels, but the engine just keeps barreling forward at the speed of light.
That is an excellent way to visualize photodisintegration. Because the energy loss per nucleon is lower, computational simulations, like the detailed models run by Murasa's team, demonstrate that ultra-heavy nuclei can survive much longer journeys through the intergalactic medium than isolated protons ever could.
I see the dominoes falling here. If the particle that hit Utah was an ultra-heavy nucleus rather than a proton, it means it could have traveled from vastly further away than the 50 megaparsec limit dictated by the GZK cutoff.
Exactly. It didn't have to originate in our immediate local neighborhood at all.
And if it originated from deeper in the cosmos, its journey time was much longer. This completely rewrites the magnetic deflection calculations, doesn't it?
It does. Remember the Lorentz force we talked about?
Mhm.
A heavier nucleus has a higher charge. Iron has 26 protons, so it has 26 times the charge of a single proton.
Right.
A higher charge means it interacts much more strongly with the intergalactic magnetic fields. Its path is deflected far more severely than a proton's path would be.
So if you trace an iron nucleus backward, assuming it was a proton, your math is going to be completely hopelessly wrong.
You'd be totally off course.
You will draw a relatively straight line right into an empty local void. But if you recalculate the Lorentz force for an atomic weight of 56 and a charge of 26, that trajectory bends wildly.
Yes, it curves completely differently.
It curves around the void, threads through completely different galaxy clusters, and points to a source millions of light years deeper in space. The void was basically an illusion created by a false assumption of mass.
The void is an artifact of the proton paradigm. By introducing an ultra-heavy composition at the highest energy ranges, the apparent paradox of the arrival directions really begins to evaporate.
The math finally works.
Right. The sources are further away, and the magnetic scattering is much more pronounced, successfully masking the true origins.
But, solving the trajectory paradox introduces a terrifying new problem regarding the source itself, and I think this is the most fascinating part of the physics.
It is where it gets extreme.
Because if the universe is throwing protons at us, that's relatively easy to explain. Protons are everywhere. Stars are literally made of them.
True.
But if the universe is accelerating the cores of elements heavier than iron to 240 quintillion electron volts, we have a massive astrophysical supply chain issue on our hands. Normal stars do not forge elements heavier than iron, right?
They cannot. The fusion process inside a standard stellar core is basically a constant battle against gravity. Hydrogen fuses into helium, helium into carbon, oxygen, neon, silicon, and eventually iron.
But iron is the end of the line.
Iron is the absolute peak of the nuclear binding energy curve. Fusing elements lighter than iron releases energy, which pushes outward and keeps the star from collapsing under its own weight. Fusing iron, however, actually consumes energy.
It's an energy deficit.
Exactly. The moment a star creates an iron core, the fusion engine stalls, gravity immediately wins, and the star collapses in on itself.
So if normal stars die the exact moment they create iron, where in the universe do you find the conditions extreme enough to not only forge ultra-heavy elements like gold, platinum, or uranium, but to then accelerate those massive nuclei to ultra-relativistic speeds?
You need a cosmic forge of unimaginable violence.
What does that look like?
Well, you are looking for environments that facilitate the rapid neutron capture process, or the R process. To build elements heavier than iron, you need to bombard an iron nucleus with a massive flood of neutrons.
How fast are we talking?
The influx of neutrons must be so incredibly rapid that the nucleus absorbs them faster than it can undergo beta decay. It simply swells into a heavy, unstable isotope and then decays into a stable, heavy element.
So where does that happen?
The research identifies three primary cosmic engines capable of both the R process synthesis and the extreme particle acceleration required to explain the Amaterasu and oh my god events.
Let's break down these three suspects. The first one is the explosive death of massive stars resulting in black hole formation. We're talking about hypernovae or collapsers.
Yes. Consider a star perhaps 20 or 30 times the mass of our sun. When its core exhausts its fuel and collapses, it doesn't just form a dense neutron core. The mass is so overwhelming that it collapses infinitely into a black hole.
Just a complete gravitational failure.
Right. And as the outer layers of the star fall inward, they form a rapidly spinning accretion disk around the newly born black hole. The sheer friction, temperature, and magnetic chaos in this accretion disk provide an incredibly neutron-rich environment.
Perfect for their process.
Exactly. Heavy elements are actively forged in the chaotic inferno surrounding the event horizon. Simultaneously, the intensely twisted magnetic fields act as a colossal natural linear accelerator.
So they forge it and fire it.
Yes. They can funnel a portion of this newly forged heavy material outward along the rotational axis of the black hole, blasting it into the intergalactic medium at velocities approaching the speed of light in the form of relativistic jets.
It's essentially a cosmic shotgun powered by a black hole. That is wild.
It is a staggering event.
But massive stars dying in hypernovae aren't happening constantly in our immediate cosmic backyard. So what is the second candidate?
Strongly magnetized neutron stars. Specifically, a subclass known as magnetars.
Magnetars.
Yes. When a star collapses, if it isn't massive enough to form a black hole, the core collapse is halted by neutron degeneracy pressure. You are left with a sphere, roughly 10 to 15 miles across, containing up to twice the mass of our entire sun.
The density is just absurd. Like, a teaspoon of neutron star material would weigh billions of tons on Earth.
It's hard to fathom. It is basically a city-sized atomic nucleus.
Right.
It is entirely governed by the strong nuclear force. Now, as that stellar core collapses, its rotational speed increases dramatically due to the conservation of angular momentum. It's much like an ice skater pulling their arms in during a spin.
We spin faster.
Right. Furthermore, the star's original magnetic field is compressed and amplified by orders of magnitude. A magnetar possesses a magnetic field of roughly 10 to the 15th power Gauss.
10 to the 15th. What does that compare to?
Well, to put that in perspective, a standard refrigerator magnet is about 100 Gauss. The Earth's magnetic field is about half a Gauss.
So a 1 with 15 zeros compared to a half.
Exactly.
But how does a strong magnetic field actually become a particle accelerator? I mean, magnets pull things together or push them away. They don't inherently accelerate particles to a quintillion electron volts unless there is an electric field involved somewhere.
Right. That is the crucial mechanism right there. Faraday's law of induction tells us that a rapidly rotating magnetic field generates a massive induced electric field.
Oh, the spinning creates the electricity.
Yes. A magnetar is spinning frantically, sometimes several times a second, whipping a magnetic field 1 trillion times stronger than Earth's through the surrounding space. This generates an electric potential capable of literally tearing heavy ions off the surface crust of the neutron star and accelerating them along the magnetic field lines out into the cosmos.
Wait, really? So the magnetar is physically stripping off its own iron-rich crust and firing it into space?
That is exactly what is happening.
So that is a terrifying image. Okay, so what about the third candidate? Because this one ties into an entirely different branch of observational astronomy that has exploded in the last decade.
The third primary candidate is a binary neutron-star merger. Imagine two of these intensely dense, city-sized neutron stars orbiting each other in a binary system.
Just locked in a gravitational dance.
Over millions of years, they emit energy in the form of gravitational waves, slowly losing orbital momentum and spiraling closer and closer together.
Which we can actually detect now. LIGO, the Laser Interferometer Gravitational Wave Observatory, catches the literal stretching and squeezing of space-time as these massive objects dance and eventually collide.
Yes. And the final collision is one of the most violent astrophysical events in the known universe. When two neutron stars smash into each other, the tidal forces literally rip them apart.
Just shred them.
You have a massive ejection of pure neutron-rich matter. It is the ultimate R-process factory. We know from observing the optical afterglows of these mergers called kilonovae that they synthesize vast quantities of gold, platinum, and uranium.
So the heavy elements are definitely there.
The heavy elements are abundant, and the violent shock waves of magnetic field amplification during the merger provide the acceleration mechanism. A neutron-star merger can also power a short gamma-ray burst, channeling extreme electromagnetic energy into narrow jets. The Amaterasu particle, if it is an ultra-heavy nucleus, could literally be the microscopic shrapnel of two city-sized atomic cores smashing into each other, hurled out of the wreckage by a gamma-ray burst, surviving millions of light-years of cosmic friction, only to end its journey by shattering against an oxygen molecule in the sky over Utah.
I want to just pause and absorb that, because we started this with a tennis ball analogy, but the reality is so much more profound than that. We're talking about the physical remnants of destroyed stars.
It really connects us to the cosmos.
And if these violent collisions and collapses are scattering ultra-heavy shrapnel all across the universe, it shouldn't be a uniform mist. It should leave a distinct architectural footprint in the sky. Like if you have factories pumping out heavy smoke, you expect to find the smoke closer to the factories.
That's a very logical assumption.
Which brings us to a massive observational anomaly that perfectly supports this ultra-heavy theory.
Right, you're referring to the dipole anisotropy.
Yes, tell us about that.
When astrophysicists map the arrival directions of all the ultra-high-energy cosmic rays detected over the last few decades, they do not see a perfectly uniform distribution.
It's not perfectly spread out.
No, the sky is not isotropic. There is a distinct asymmetry. We observe a higher flux, basically a greater concentration, of these extreme events originating from one half of the sky compared to the other. Specifically, the flux from a broad region in the southern sky is significantly higher.
Meaning the Earth is basically getting bombarded more heavily on one side?
Yes. Now let's look at why this is critical evidence for the ultra-heavy theory.
Okay.
If these particles were lightweight protons originating from incredibly distant sources across the universe, the intergalactic magnetic fields would scramble their paths so thoroughly over billions of light years that any original asymmetry would be washed out completely.
They'd just be coming from everywhere.
By the time they reached Earth, the sky would look completely uniform.
It's like dropping dye into a massive churning ocean. Eventually, the color diffuses perfectly evenly.
Exactly. But if the cosmic rays are ultra-heavy nuclei, they suffer from photodisintegration. They have a survival limit. While an iron nucleus can travel further than a proton, it cannot travel forever.
Right, it's losing boxcars.
Therefore, the ones we are detecting must still originate within a relatively constrained cosmic volume. Our local supercluster, for instance. And on the scale of our local supercluster, matter is not distributed evenly. Galaxies, and therefore the neutron star mergers and hypernovae within them, are clumped together along vast filaments, separated by voids.
So the asymmetry we see in the night sky isn't a random glitch. It is a shadowy reflection of the actual distribution of matter in our local universe.
It's a map.
The fact that one side of the sky is hotter with cosmic rays implies that there is a higher concentration of these cosmic forges, these black hole collapses and magnetars, in that general direction. And the only way the particles could maintain that directional imprint without getting completely randomized is if they possess the heavy mass and rigid momentum to push through the magnetic fields with some of their original trajectory intact.
The mathematics align perfectly. By calculating the mass-to-charge ratio of iron, the rate of photodisintegration, and analyzing the observed dipole anisotropy, scientists can begin to place stringent constraints on exactly how these ultra-heavy particles contribute to the overall cosmic ray spectrum.
It's tying it all together.
The asymmetry essentially demands a heavy composition at the highest energies. It is the only physical model that currently balances the equation of survival distance, magnetic deflection, and source distribution.
Which brings us to the most exciting part of this entire field, which is how we actually prove it. Theoretical models and computational simulations are brilliant, but physics demands observational proof.
We need hard data.
Right. If the universe is throwing iron at us instead of hydrogen, we have to catch it and weigh it. But as we established earlier, the particle obliterates miles above our heads. So how do you weigh a ghost? How do you distinguish between a proton air shower and an iron nucleus air shower when all you see is the resulting cascade of secondary particles hitting the dirt?
This is the immense engineering challenge facing next-generation observatories. The research highlights the critical importance of facilities like Auger Prime, which is a massive upgrade currently being implemented at the Pierre Auger Observatory down in Argentina.
And the Pierre Auger Observatory is the largest cosmic ray detector in the world, right?
It is. It covers an astonishing 3,000 square kilometers of the Pampa Amarilla.
3,000 square kilometers. That's like the size of Rhode Island, just covered in sophisticated ghost traps. Let's talk about the specific architecture of those traps. Because they aren't optical telescopes. You aren't looking through a glass lens waiting to see a flash of light.
No, you're looking for secondary particles hitting the ground, specifically muons and electrons. The base architecture of the Auger Observatory consists of 1,660 water Cherenkov detectors.
Water tanks.
These are large tanks, each containing 12,000 liters of ultra-pure water, spaced out on a massive grid.
But why water? What happens when a cosmic ray fragment hits a tank of pure water?
We are looking for Cherenkov radiation. When a secondary particle, like a muon from the air shower, passes through the water, it is actually traveling faster than the phase velocity of light in that specific medium.
Wait, I need to clarify that, because saying faster than light usually triggers a lot of alarms. Nothing travels faster than light in a vacuum, but light slows down when it passes through water, right?
Correct. The speed of light in water is roughly 25% slower than in a vacuum.
Huh.
These highly energetic muons are traveling at 99.9% the speed of light in a vacuum.
Oh, I see.
So when they hit the water tank, they are vastly exceeding the local speed limit of light within the tank. This creates an electromagnetic shock wave, analogous to a sonic boom created by a supersonic jet.
A light boom.
Exactly. This shock wave manifests as a faint, cone-shaped flash of blue light, which is Cherenkov radiation. Photomultiplier tubes inside the tank detect this flash, telling us exactly when and how hard the secondary particle hit.
That is just brilliant. So the water tanks give you the footprint of the shower. You see exactly how the energy was distributed across Rhode Island.
And that is paired with fluorescence detectors, which are specialized telescopes that look out over the night sky, completely in the dark, watching for the faint ultraviolet glow of nitrogen molecules in the atmosphere.
The air is glowing.
Yes, being excited by the cascade tearing through the air. The fluorescence detectors give us the longitudinal profile, basically how the shower developed as it moved downward through the atmosphere.
But if you have the water tanks and the atmospheric glow, why do we need the Auger Prime upgrade? What does the upgrade actually add to help us solve the ultra-heavy mystery?
The upgrade is entirely focused on composition. We need to conclusively distinguish between a primary proton and a primary iron nucleus. The key to telling them apart lies in the ratio of muons to electromagnetic particles, meaning electrons and photons, in the resulting air shower.
How does iron change the ratio?
Because an iron nucleus is essentially a bundle of 56 nucleons interacting simultaneously in the upper atmosphere, it creates a shower that develops higher up and produces significantly more muons at ground level compared to a proton shower of the exact same total energy.
So an iron air shower is basically a muon-rich shower.
Exactly. To measure this precisely, the Auger Prime upgrade places surface scintillator detectors directly on top of every single water Cherenkov tank.
On top of all 1,600 of them.
Yes. Scintillators are highly sensitive to the electromagnetic component of the shower, while the water tanks below are highly sensitive to the muons. By combining the data from both detectors at the exact same location, scientists can disentangle the muon signal from the electron signal with unprecedented accuracy.
It's like multi-messenger forensics. You aren't just measuring the total splash, you are basically separating the water from the oil to figure out exactly what hit the surface.
And furthermore, they're adding radio antennas to detect the radio pulses generated by the shower particles moving through the Earth's magnetic field. It is a stunning layer cake of observational data.
It sounds absolutely necessary, though.
It is absolute necessity. To conclusively prove Maras's theory and solve the 60-year mystery of these cosmic voids, Auger Prime and other proposed facilities like the Global Cosmic Ray Observatory must catch the undeniable, mathematically rigid signature of a muon-rich, heavy nucleus cascade at these extreme 100-plus exelectron volt energies.
We need the smoking gun.
Right. The theoretical framework has caught up to the anomalies. Now the engineering must provide the irrefutable proof.
Man, when you look back at the entire scope of this journey, it is genuinely humbling. We started by trying to understand a single solitary microscopic particle hitting the Utah desert with the brute physical force of a tennis ball.
A single data point.
And that single detection forced us to stare at an empty, terrifying cosmic void and realize our fundamental math was completely broken. To fix the math, to trace the Lorentz forces correctly, we had to fundamentally upgrade our understanding of the messenger itself.
We had to rethink everything.
We had to realize that we aren't just being bombarded by the lightweight chaff of the cosmos. We are likely being bombarded by the heavy, iron-rich remains of the universe's most extreme cataclysms.
It really demands a profound respect for the violent, dynamic reality of the cosmos. What we perceive from Earth as a quiet, static, starry night sky is just an illusion.
A very peaceful illusion.
The universe is a canvas of unimaginable destruction and creation, broadcasting its history across billions of light years. We are standing in the crossfire of neutron star mergers and black hole formations, surrounded by the physical shrapnel of these events.
And it leaves you with something to truly mull over the next time you step outside and look up. Because right now, as you sit there listening, the universe is operating at a scale that completely ignores human boundaries. It ignores our engineering, our biology, our perception. Very. If the Amaterasu particle is just a single atomic messenger carrying the violent, explosive secrets of a dying, massive star from millions of light years away, what kind of cosmic history is passing right through the room you're in, completely unnoticed at this very moment? The universe is constantly speaking to us in a language of extreme energy. We are just finally learning how to translate the heaviest words.